One of the primary responsibilities of an operator is to ensure the refrigeration system is operating efficiently and meeting the expected facility refrigeration loads. This is only possible if the system is properly maintained. Therefore, an operator must see to it that maintenance is performed. This might mean that the operator is routinely turning wrenches, that he manages a team of technicians, or that he oversees the contractor providing this essential function. Nothing lasts forever. All mechanical equipment has an expected lifespan that can be prolonged or shortened based on how it is maintained. In the U.S. Department of Energy's Operation and Maintenance Best Practices Guidebook, 4 distinct types of maintenance programs are described. Reactive maintenance is the attitude that we'll run it until it breaks. Reactive maintenance is attractive because the maintenance budget forecast is low since tasks are not performed on a planned schedule. Furthermore, reactive maintenance requires minimal staff. Reactive maintenance can work quite well on new equipment because we expect that there will be a prolonged period of fault-free running. Unfortunately, the downsides of reactive maintenance can be quite extreme. First, we cannot know in advance when something will break, so this approach to maintenance often results in unplanned downtime to fix broken equipment. Second, small matters that could have been dealt with during planned maintenance are ignored, which may allow them to escalate and become a much bigger and more expensive repair. Preventative maintenance is a familiar term to many. In a preventative maintenance approach, tasks are performed preemptively on a calendar basis or a runtime basis. Rotating the tires on your car every 5,000 miles is a preventative maintenance mindset. Preventative maintenance reduces unplanned downtime caused by surprise or reactive failures. In addition, studies have shown that preventative maintenance improves energy efficiency and prolongs equipment lifespan. The downside of preventative maintenance is that it requires resources, namely maintenance staff and money to implement. Predictive maintenance is a less familiar term, but one all operators should be familiar with. Predictive maintenance utilizes measurements to detect the onset of equipment failure prior to any noticeable degradation. In the refrigeration industry, ultrasonic thickness testing, vibration analysis, and oil analysis are examples of predictive maintenance. Predictive maintenance is exceptionally useful at identifying issues while they are still small and less expensive. In other words, predictive maintenance helps to reduce the occurrence of catastrophic failures. The downside of predictive maintenance is that it requires more expensive tools and a higher level of training to implement. For example, employing vibration analysis on a screw compressor requires expensive equipment and the training necessary to use the equipment and interpret the analysis results. Reliability-centered maintenance is a term used to describe an approach to maintenance that merges the 3 other philosophies. Reliability-centered maintenance recognizes that not all equipment failures are equal and therefore aims to place resources to the best use. For example, the quantity of oil in a reciprocating compressor is substantially less than that of a screw compressor. Therefore, replacing the oil annually on a reciprocating compressor, which is an example of preventative maintenance, may be employed while oil analysis, a form of predictive maintenance, is done on the screw compressors only. For inexpensive, low-risk items, reactive maintenance may still be used in a reliability-centered maintenance program. For example, if a system has 5 condensers and 1 fan belt breaks, the consequences are minimal. Therefore, a facility may opt to keep extra belts in stock and replace them when they break instead of replacing the belts on a calendar or runtime basis. The big idea is that not all maintenance activities are equal. An operator must understand what is critical to safety and overall system performance and make sure that those tasks are being performed. For ammonia refrigeration systems, the RMP and PSM regulations mandate that owners implement a mechanical integrity or MI program. Typically, the MI program will be designed to address the inspection, testing, and maintenance, or ITM tasks that are required by the following: the equipment manufacturer, recognized and generally accepted good engineering practices, or RACGEP, and prior operating experience.
One of the challenges of an inspection, testing, and maintenance program or a mechanical integrity program for a refrigeration operator is knowing which RACGEPs to use or which recognized and generally accepted good engineering practices to refer to. So what is a RACGEP? Well, it's really an industry document. And even in my career, I've seen quite a change in RACGEPs. When I started my career in ammonia refrigeration, IIAR Bulletins 109, and 110 were widely referred to as RAGAGEP for operation and maintenance. Bulletin 110 addressed a wide variety of topics, including startup, but also operation and maintenance. And 109 was probably even more famous, mainly because in the back of the document, there was the widely referred to B109 checklist, which has been widely used as a checklist for annual mechanical integrity inspections. But due to some shortcomings in these documents, namely they didn't use normative languages like shall and must, and there was a lot of optional wording like you may do this or it's recommended to do that. They were done away with, and in 2019, IR published Standard 6, which is the inspection, testing, and maintenance standard for ammonia refrigeration systems. Now, for the first time, we had a standard that addressed the minimum requirements for an ammonia refrigeration system as it relates to these activities. But it didn't just stop there, because everything progresses, and just 6 years later, a new standard was published or updated, Standard 6, same cover, but the 2025 version. So in a sense, there is a bit of a moving target, but it's a good thing, because as an industry, we're always refining, correcting, and focusing our attention on what's important. So it's important that the operator understand this and know which RAGAGEPs they're following.
As with SOPs, ITM requirements will be equipment and facility specific, but some tasks are generally universal. Compressors typically require the most ITM attention from an operator. Daily, the following must be monitored on all compressors: suction pressure, discharge pressure, oil level, oil leaks, alarms on control panel, and abnormal sounds and vibration. Additional parameters must be monitored on screw compressors such as oil temperature, discharge temperature, oil filter differential pressure, slide valve capacity percentage, and motor amperage. Annually, compressors must be inspected for proper anchorage, surface corrosion, drive alignment, and unloader operation. Functional tests must be performed annually on the following compressor safety devices: low suction pressure cutout, high discharge pressure cutout, high discharge temperature cutout, low oil pressure cutout, and high liquid level cutout. Maintenance for a compressor will depend on many factors. An operator must be prepared to ensure the following maintenance tasks are performed as necessary: adding oil, changing or cleaning an oil filter, performing oil analysis, changing oil, replacing the shaft seal, and lubricating bearings. Condenser ITM tasks cover a wide range of activities. Weekly, condensers must be inspected for the following: water supply is functional and abnormal sounds and vibration. Annually, the inspection should be more thorough and verify the water distribution system is working, anchorage is adequate, fans, shrouds, and hubs are in good condition. The water treatment system for evaporative condensers must be tested at least monthly to ensure it is within tolerable limits. The water sump on an evaporative condenser will require periodic cleaning based on the location and duty of the condenser. Other maintenance tasks that the operator must be aware of include replacing fan belts and lubricating fan and pump motors. Air cooling evaporators should be inspected weekly for abnormal sounds and vibration. At least monthly, the evaporator should be inspected for excessive ice buildup. Every 6 months, a thorough inspection should check for damage to external parts, fan blade cracks, dirt buildup, adequate protection from traffic, and obstructions in the drain pan. Air cooling evaporators do not have many testing requirements. However, it is recommended that a defrost cycle be observed every 3 years. Maintenance on air cooling evaporators is straightforward. The tubes and fins should be cleaned at least annually, and fan motor bearings lubricated as recommended by the manufacturer. Pressure vessels must be inspected at least annually. However, for the main system vessels, such as high-pressure receivers and recirculators, it is recommended that they be included in the system lock inspection. At minimum, the annual visual inspection will check for surface corrosion and pitting, damage to sight glass metal surfaces, moisture in the insulation that could lead to corrosion under insulation, damage to insulated vessel's protective jacket, paint degradation, proper anchorage and support structures, excessive vibration when liquid is being supplied, and a legible ASME stamped nameplate. Depending on the application of the vessel, specific tests may be required. Vessels that supply vapor directly to a compressor will be configured with a high liquid level float switch that must be tested at least annually for proper operation. Every 5th year, ammonia vessels should be assessed by a qualified inspector to determine if non-destructive testing, or NDT, should be performed. Ultrasonic thickness testing and radiographic testing are common methods of NDT employed on ammonia pressure vessels. Vessels used to collect oil should be drained as needed as part of a pressure vessel maintenance. Additionally, carbon steel vessels should be cleaned and painted periodically to protect the metal surface from corrosion. Heat exchangers require many of the same ITM activities as pressure vessels. Since these units are often used to cool a secondary coolant, proper secondary coolant flow should be verified annually. If a heat exchanger is used for food processing or beverage application, it will need to undergo clean-in-place, or CIP, in accordance with the Food Safety Program. Plate and frame heat exchangers can be disassembled for a thorough cleaning, although this is rarely necessary. Shell and tube heat exchangers can be mechanically cleaned using tube brushes if scale buildup is severe. Refrigerant pumps should be regularly inspected. At minimum, weekly inspections should ensure that the pump discharge pressure is acceptable, open drive pump shafts are adequately guarded, and the oil level in the reservoir is acceptable. Hermetically sealed pump bearing wear monitor is in the acceptable range, and the pump is free from abnormal sounds and vibration. Annually, each pump should be inspected for surface corrosion and pitting and proper anchorage. Pumps installed on a recirculator package will be interlocked to cut out if the liquid level in the supplying vessel drops too low. Annually, the low liquid level or cavitation cutout must be tested. Maintenance tasks for pumps that an operator must be aware of include replacing belts and lubricating motor bearings. Like pressure vessels, refrigerant pipes must be inspected annually. During the inspection, the inspector will look for surface corrosion and pitting, moisture in the insulation that could lead to corrosion under insulation, damage to an insulated pipe's protective jacket, paint degradation, proper pipe labels, adequate piping support, including sway braces, and excessive vibration. Every 5th year, ammonia piping should be assessed by a qualified inspector to determine if non-destructive testing, or NDT, should be performed. Valves are typically inspected with the refrigerant piping. In addition to verifying the standard items such as surface corrosion, valve inspections must look for corrosion or paint on the valve stem and loose bolts on flanged connections. Valve maintenance must not be overlooked. Annually, emergency shutoff valves must be exercised and lubricated. Other valves require the same maintenance, but on a 5-year frequency. Refrigeration relief valves should be inspected annually to verify that the relief valves have the correct set pressure and capacity. The ASME seal is unbroken. The relief valve has a legible nameplate. The installation date is within 5 years from the date of the inspection. No stop valve is installed upstream of the relief valve. Any stop valves installed downstream of the relief valve are locked open. The size of the discharge piping is properly engineered to prevent excessive back pressure during a release, and termination of relief valves is adequate. For ammonia, the termination pipe must not be within 20 feet of a building opening and must be 15 feet above grade or 7.25 feet above a roof or platform. Maintenance on relief valves consists of replacing the valves every 5 years and draining water from the discharge piping annually where that provision is provided. Emergency stop switches, or e-stops, must be inspected every 6 months to verify that the switch is in good condition and properly labeled. Annually, the switch must be functionally tested to confirm all associated equipment is de-energized when the switch is activated. Most gas detection manufacturers recommend that gas detectors be calibrated every 6 months. In addition to calibration, the detectors should be functionally tested annually to verify that the interlocks and alarms are functioning as designed. During each calibration, the detectors and alarms should be inspected to verify that signage is installed and detector enclosures are in good condition. Eye wash and safety showers are important resources for administering first aid. As such, the combination units serving the refrigeration system should be tested weekly to flush the lines and ensure water flow is adequate. Annually, these units should undergo a more thorough test to ensure the units are installed in accordance with ISEA Z358.1. Among other things, the annual test will check for proper flow rate, flow pattern, and water temperature. Machinery room ventilation systems should be inspected routinely to ensure the ventilation system is operating as designed. Annually, the system should be functionally tested to ensure temperature-controlled ventilation is working, emergency ventilation is activated at the proper gas concentration. For ammonia, this is typically 150 ppm. The emergency ventilation switch works, the ventilation fans provide adequate airflow, intake louvers are functioning as designed, and all audible and visual alarms are working.